ಅರ್ಥಲ್ಲ. ಅಲ್ಲಿಂದ hello, hello, testing, hello, check, hello. செஞ்சு வாங்க, மேலே வாங்க. இல்லை, அங்கே நான் அட்ஜஸ்ட் பண்ணணும். நீங்கள் யாரோ ஒருத்தர் பேசினா தான் நாங்கள் அட்ஜஸ்ட் பண்ண முடியும்.
Hello, 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 hello.
Okay. Okay.
Hello, 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 hello.
Hello, testing, check, mic check. Hello.
Kanan? சரி தோணுங்க. Helping once. வந்து கவியை வந்து பேசியிருக்காங்க. சொல்ல சொன்னாலும் முக்கிய யாருமே இல்லைப்பா. இருக்காங்க. ஓகேவா? பண்ணலாம். வந்து
சரி 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 சரி
Good afternoon to everyone present here. On behalf of Department of Applied Mathematics and Computational Science, I welcome all of you for today's lecture. Now I call Dr. R. Indumadi, Associate Professor, Department of Applied Mathematics and Computational Science, to introduce today's speaker.
Good afternoon to everyone present here. The speaker of the day, Dr. Raja Venkateswaran, is the Director of Engineering in Qualcomm Innovation Center. He leads the Snapdragon LLVM CPU toolchain effort, which focuses on adding performance and code size optimization to LLVM toolchain to deliver advantage to Qualcomm customers. Dr. Raja has been working on compiler and toolchain related technology for the past 20 years. Before joining Qualcomm, he worked in the Texas Instruments compiler team. Dr. Raja has his bachelor's degree from PSG Tech Coimbatore, master's from Indian Institute of Science, and PhD from University of Virginia. We are privileged to have such an eminent speaker to deliver his talk on Scalable Vector Extension ISA in ARM. To my small knowledge, the ARM architecture specifies a set of rules that dictates how the hardware works when a particular instruction is executed. An instruction set architecture ISA is a part of the abstract model of a computer that defines how the CPU is controlled by the software. Today's talk introduces the ARM's new vector instruction set known as the Scalable Vector Extension, shortly termed as SVE. The talk provides an overview of SVE with examples and details the advantages of SVE over older neon vector ISA. It also compares and contrasts with ISA capabilities of SVE and neon, as well as discusses compiler challenges targeting SVE. I now leave the dais open to Dr. Raja to inspire us on the specified domain. Welcome, sir.
Thank you, everybody, for the great welcome. Really appreciate it. So it's first of all, I'm really excited to be back in PhD Tech. You'll probably guess my age if I tell you when I graduated, but that's okay. So I graduated in '93. I think I was the third batch of CS. At that time, we did not have a department. So we were part of the electrical engineering department. And so there's a lot of memories. And I was just talking to Dr. Engels, and it's great. So I'm really happy to be here. So a couple of things first. Whatever I'm going to talk about is public domain information. So as in, I'm not going to tell you anything new. You can probably Google and find out. But I thought it would be a good topic because the scalable vector extension itself is fairly new. And it's not that popular yet. And I can talk about that a little bit as well. And the other thing is, I don't want this to be just me going on. And I know it's post-lunch is a hard session to focus. So please ask questions. I always tell everybody there's nothing called dumb question. I'll probably give a dumb answer, but please ask any question. And I'm here to help, there are people from different backgrounds with different kinds of understanding of different areas. So definitely like to hear any and all questions, and I'll be happy to answer them. So please feel free to stop me in the middle if you have a question, and I'll address it. So we don't have to have all the questions at the end. The other thing is, I will talk a little bit about what Qualcomm is doing with SVE towards the end of the presentation. I don't know I want to put it in the slides, but I'll be happy to talk about any specific questions you have. So I'll introduce the authors of the presentation. So the presentation is a joint effort by my teammates and myself. Chris is a staff engineer to me in my team, and he is the technical lead for the auto visualization effort. I'll talk a little bit about auto visualization later. And then Eli Friedman, for those who are familiar with LLVM community, Eli is one of the most prolific contributors in LLVM. He's extremely active. He has authored patches, and he's a very active reviewer. One of the smartest minds in LLVM, represented with my team. And of course, Madam gave an introduction about myself. Thank you for the warm welcome. So, what's Qualcomm Innovation Center? I don't know how many people know what Qualcomm does. So I'll talk about it a little bit. So Qualcomm is, let me put it this way. So there's pretty much most of the cell phones we have today. Not all the same way. So if you have an Android phone, chances are it has a Snapdragon chip in it, which comes from Qualcomm. If you have an iPhone, the main technology comes from Qualcomm. So Qualcomm has been leaders of modern communication for a very long time. And over the last 10 years or so, Qualcomm has also been making SFCs, or system on chips, which is powering Android phones. So I'm part of Qualcomm Innovation Center, which is basically our work on open source. So Qualcomm Innovation Center was started to do open source computing, and we wanted to make sure that we are properly interacting with open source software. So any group that works mostly on open source, like myself, I work mostly on LLVM toolchain. We are part of Qualcomm Innovation Center, just like Rahul is part of Qualcomm Innovation Center in Hyderabad. So, you want to wait for a couple more minutes, or? So, please do stop and ask questions. So I'm not going to just jump into what is SVE first. I'll talk about what is what I'm talking about first. What is vector? What is SIMD? That level. It's not because we are first years or second years. It's mostly because a lot of people do not necessarily have a background in vectorization or vector instructions or vector computing. So a couple of slides that we cover the background will help. Talk about the instructions and features, and very briefly on the single component challenges that we had to come across. As I said, please feel free to stop me and ask me any questions or look at questions online if someone is monitoring the students. SIMD. So SIMD is a fancy acronym for single instruction, multiple data. And I remember sitting in one of these conference rooms almost 30 years back, and I heard this term first. At the time what it was. Hopefully I have some idea now. Typically, no computation operates on one piece of data. There is going to be a lot of computation that is going to need to operate on multiple pieces of data at the same time. So if you look at a program, for example, you do control flow, data flow, you do some computation, but also there's not code that you're going to write that is going to say, I want to do the same operation on all the elements of an array. I want to add elements of an array, for example. And just that's single multiple pieces of data, but I don't know how to make it run on the hardware. So that is one challenge that SIMD is trying to address. And there's a lot of hardware over the last 20 years that has come up across the spectrum. I'm not just talking about mobile just because I'm from Qualcomm. If you go to performance computing, supercomputing, is one purpose of SIMD, right? You don't need a supercomputer to run world, but you don't need a supercomputer to it's vector modeling, mathematical modeling, machine learning, which is the latest buzzword, conformance models, all those things. So it takes a single instruction that says do the same operation on multiple pieces of data and then produce the result. So let me give a more concrete example here. So the data is stored in each unit, what's called a vector register. So you're familiar with what is a register. Register is, an integral part of the CPU that holds some data. It could be, character, char, float, some unit, some type of data. A vector register holds multiple pieces of the same type of data. So if you have a vector register of characters, then you can have, if your register is 128 bits wide, you can have up to 16 characters or 8 shots or 4 integers, for example. Okay, if you can use this vector register to generate code, then I will provide you what is called a vector instruction that will operate on these vector registers. So instead of just saying A, B, and C, and put it in C, you're just going to say vector add A and B and create the result in C. Okay. So you have vector registers. In this case, imagine this is a vector of integers, and typically, on a 32-bit machine, you have each integer is 32 bits, and then you're going to say, okay, I'm going to add these two vectors and produce the result. So if you have, so now a vector scalar. So if you do this operation as scalar instructions, you have to load 4 integers for vector A, 4 integers for vector B, 4 addition operations, and 4 store instructions. So that's about 13 instructions. And you can do all that in one instruction. The addition in one instruction, the load store in 2 or 3 instructions. So you basically save effectively 3 times the computation by using vector unit. If there are any questions on this, please feel free to ask me. Yes. Usually not. So, if you're doing this in hardware, most of the heavy lifting is done by the hardware. So if you want to think about on the hardware side, for example, you need to have your memory line should be able to load 4 integers at a time, right? So the instruction is not just providing instructions; it's providing capabilities to be able to load and store many units of data, right? So, 2010 hardware probably, is optimized for loading and running one integer and one float, right? But after that, they have built up the architecture so much that you can. So that's add complexity as a hardware designer when you design the architecture. So it is transparent. It's the performance. Okay. So all this, we're doing this in register. So remember, all this is not in memory. I mean, if you remember your architecture courses, you'll see that memory is extremely slow and expensive. So you want to hold this as part of the core architecture, and usually the size is fixed. So which means that as a hardware designer, you want certainty. You want to know exactly what is the size of your register. If you don't know what is the size of register, you cannot design hardware. So early hardware basically said, okay, the size of the register is 128 bits, and that's the first version of ARM I'll talk about in a minute. And then it said, okay, the size is 128 bits, and it can hold different kinds of data and different number of elements depending on the size of the type. So just to reiterate what I said, a 128-bit register can hold 16 8-bit data units or 8 16-bit data units. So which means that if you're operating on smaller type elements, you'll probably get better performance than if you're operating on bigger type elements. So this is just a pictorial representation of a 128-bit register can hold different kinds of data. So ARM came out with something called Neon, and it's all caps, and it's a trademark. So Neon is, the colloquial version is it's kind of a live. So they came up with this Neon vector processing engine, which is basically a 32-bit. Original implementation was 32-bit in ARM v7. So ARM, for those who are familiar with the ARM architecture, the first generation ARM is ARM v4. Then it came up with the 5, 6, and 7. And ARM v7 is where they really focused a lot on 32-bit performance, because before that, ARM was primarily focusing on microcontrollers, running smaller images, and those kind of details, which was not performance-driven. Because if you look at SoC that Qualcomm or anybody else makes, can anybody guess how many ARM CPUs are there? Don't be afraid to guess. Everybody knows about the central the application processor. That is the big one that takes a lot of space and a lot of power. But typically there are about 13 different ARM cores in an SoC, 1-3. And each of these cores have a very specific purpose. They run a single image. There's no memory map, MMU or anything like that. They directly access the system, and there's also protection around them. So it's not like average user can load an image in there. So most of these images can be loaded only at boot time and things like that. So there are a lot of restrictions on how that can be accessed, but they are not meant for general purpose access. So the CPU is what is meant for general purpose access. So ARM was making a lot of money just making microcontrollers, and that's where their core of their business used to be before 2008. And that's why, if you know, 2008 is the time, right now, everybody takes cell phones for granted. But in 2008, there was no smartphones at that time. Right? When Apple came up with it, everybody was like, wow, I need to have an iPhone. Right? And then Android followed, and then had to follow it, because everybody decided today there are no more devices in the world than Intel devices. That's the truth. And it is mainly because of the explosion of cell phones. So this is a critical part of that. So ARM v7 was the first architecture that had a focus on performance. And then they came up with something called Neon, which is the vector processing unit. They had 16 128-bit registers. And then these registers can be used at, if I remember right, they couldn't handle the floating point in the first double floating point in the first two versions. Then they came up with something called ARM v8, which is the 64-bit version of ARM processor, and that also had a little more registers. There are 32 registers. So what is so special about Neon? Okay, so how many have looked at any image processing algorithm? So image processing algorithm is, somebody takes a picture of this room, and you have, depending on how good your camera is or how many megapixel is, you're going to have an array of pixels, right? And what is a pixel? A pixel is just a combination of red, green, and blue colors, right? And you put millions of these together, you get something that the human being can understand. So what I'm showing here is how a picture looks like in real memory. Red, green, blue, red, green, blue, red, green, blue. That's what it is. It's an array of red, green, and blue. And when you go look at a picture on your phone or a computer, there's so many algorithms. When you load the software that loads the image, there's a lot of processing that is happening behind the scenes that we are not aware of. One of the things is something called saturation, for example, where if a particular color is beyond a acceptable value. So typically colors have a value 0 to 255. So from just going down to the computer science level, if a color has a value of, if you manipulate a color and get a value of 300, that value makes no sense. So there's something called saturation that happens, which brings the value to 255, right? And you want to do this saturation not on every image pixel here, one at a time. You have to wait for 10 minutes to see your picture. It has to happen all at the same time. So let us think of a computation. So let me do this. So if you look at the code on the right, right? So what it does is it adds up all the red, R plus equal to AI. It takes all the red colors, adds them up. It takes all the green colors, add them up. It takes all the blue colors, add them up. If you do this one by one, you will end up with, with extremely expensive computation. You have to load each of these elements of the vector. You have to add them, and then, you have to probably unroll the loop so many times. So there is something called a gather load feature in Neon. What it does is it basically says, I know what you're doing here. You're just loading from contiguous memory, but you're doing different things with them. So if you look at this, it's a load 3 instruction, which means it's going to load from 3 different lanes into 3 registers here. With all the X0 is the base pointer. So it points to the start of memory, and then it's going to say, I'm going to load first value into V0, the first element of V0, second value into V1, and then third value into V2. And then I'm going to go back and do this again. And this S basically specifies the size of the data, and then the .4 indicates how many elements are there. This code is not written by human. This is a compiler generated code. If somebody wants to make a note of that, I'll answer that later. It's a quiz to make sure you guys are all awake. So the opposite of gather load is scatter store, which means that you compute some value and then you want to write it back into memory. You just use a single instruction to do this. There's a lot of effort going on in, if you look at Android code, which is open source, for example, if you go look at the image processing algorithms, or you can go look at any of the camera image processing algorithms, there's a lot of effort put in vectorization. And they can use every feature available in the hardware to do this. So the other one I talked about is what is called, Neon has simple control flow vectorization. Control flow is one of the most difficult things to vectorize because it's all or nothing. Either the compiler needs to very well understand how the control flows and make sure that the control flows the same way for every piece of data, which is not easy. I'll talk about that when I come to SVE. So in Neon times, basically, they did not think too much about control flow vectorization. They also worried about the complexity in the hardware. So they had simple control flow vectorizations. For example, minimum, maximum, right? If you compare 2 vectors and you want to pick up the minimum, right, it's easier to do. So a typical min-max C code looks like this. Right? If you're comparing 2 arrays A and B and you want to store the maximum of those value in array C, this is what it's going to look like. And before Neon, it's impossible to optimize this in a meaningful way that you can get a result in a reasonable time. But Neon, I had this thing called S-max instruction, which basically says, I'm going to compare 2 vectors and pick up the maximum element of the corresponding elements of each vector and store it in the result vector. So this is probably, I would say, 10 to 15 times faster than a scalar code. And this is one of the key things that a lot of algorithms took advantage of. So what's wrong with Neon? Right, it looks good. It does most of the stuff. The problem is people in the high performance world started complaining because now you have ARM v8, which is a 64-bit processor. Now you have new manufacturing technologies, which means that in the same area, you can pack more computation. But Neon is still 128-bit. They don't want to do 128 bits anymore. I'm talking about high performance computing world, not Qualcomm. Qualcomm is not in high performance computing. Qualcomm is in mobile computing. So if you talk about supercomputing centers, defense, in India, there are a lot of, defense research that goes on, and or modeling, for example, even AI, right? If you're developing a training model, right, you want that training model to run as fast as you can, right? And you cannot, and you need a much more powerful thing. It's basically Neon as an ambassador car. You cannot go to race with an ambassador car, right? You need a Ferrari. So that's when they said, okay, we don't like Neon because it's not doing what it needs to be, what we need today. So they came up with something that will scale. What does that mean? So, which means that it should work well for mobile code, but the same processor should work, or the same should work equally well on a high performance code. So it should be able to run it, the car example is it should be able to run at any speed I wanted to run it without changing anything about the car, right? You don't want, so this is a bit tricky. I'm not saying the hardware does not change. I'm just saying that the software does not have to change. Okay. The other problem is control flow is very difficult to vectorize. So what we saw is only a couple of examples of control flow, which is useful but not complete. I'll go through some of these other examples, but the half float is very important because machine learning is really picked up, right? And if you look at bfloat 416, for example, which is one of the new standards that Google is pushing, there's humongous amount of training data. I know if you like cat pictures, and you'll probably see Google, optimizing cat pictures and identifying cats and dogs. They go through millions of pictures, and they have to feed through all this through algorithm. And to speed it up, they're going to use floating point, but a smaller precision floating point. That's called float 16. And you want this to run as fast as you can, right? Because the training model has to be really good so that your inference model is available more quickly, right? You cannot, and then the training models are not going to run on your laptop or your phone. They run on extremely powerful machines, and the inference model that they figure out runs on your end device. So the training model has to be good, but very fast. So this is a challenge because Google said, we do this and your hardware is not good enough, right? So what did ARM come up with? They came up with something called Scalable Vector Extension. So what they did was just like any other hardware vendor, they said, oh, we want to keep Neon because we know a lot of people are using it and they're going to get super mad if we get rid of Neon. So we go to add another vector unit called SVE, or Scalable Vector Extension, right? And what that means is it's going to be scalable across cores. So they basically said the instruction set does not know the size of the vector. The instruction set has no idea what the size of the vector is. So in Neon, if you do 2 vector adds, the vector length is 128 bits. You know the size of the types, so you know how many elements are there. In SVE, you have no clue. The instruction set does not know because the hardware designer has figured out whether he wants to put a 128-bit vector or a 2048-bit vector. So it can actually go up to 4096 bits. So high performance computing. So I was in a conference and I was talking to a few people from, say, Fujitsu, and they were showing me a piece of hardware that actually has 2048 bits vector. I was like, wow, that's amazing, right? So they were basically saying, I'm not able to get the performance out of this. So how do you optimize? So they were harassing the ARM guys. So this is very important from a compiler perspective. For those who are familiar with the compiler considerations, it's very hard to think about it because the compiler needs to know what is the size of a data type, or what is the needs to know the type of the register. If you don't, your optimizations are not going to work very well. And then the other thing they did was they came up with a large instruction set, because you cannot keep coming up with a new instruction set every 2 years. It's not a new phone. It takes several years for a new instruction set to be understood, adopted, and optimized in the industry. So they wanted to come up with something that's probably good for another 15, 20 years. So they just decided to put all the capabilities, including machine learning, DSP, machine learning, a lot of you are teaching or learning machine learning here, but primarily it comes down to how fast you can do matrix multiply, right? That's what it is. So, or, specific operations, but operating on matrices. So they came up with all these different instructions that provided the capability. Of course, it's up to the compiler and the user to figure out how to use these instructions. So they came up with something like SVE2. So a lot of people used SVE and said it's great. This feature in Neon, I want to use it in SVE. So just like any other hardware vendor just gave in and said, okay, I'll give you more capabilities, and they call it SVE2, and they charge more money for it. So the difference between vector register for Neon and SVE is, in Neon, you know exactly what is the size of the vector, SVE don't. When I say you don't, I'm talking about the compiler. The compiler does not know. But so I think Qualcomm has already released one of their first ARM-V8 chips with SVE capability. I think it's got 128-bit vectors. But if you Google and find out, probably, as I said, Fujitsu already has a solution. I don't think anybody can buy it, but it probably has about 1024 or 2848-bit vector. So depending on the size of the vector, it can hold more data items. So 256-bit vector can hold 30 characters as opposed to a Neon, for example. So they came up with 32 scalable vector registers, and there's something called registers, which is required for control flow. I'll talk about predication in a minute. Predication is the solution for solving the control flow problem. So remember what I talked about earlier, which is, you cannot do complex control flow. You cannot say, I want to apply my operation only on element 1, 2, 3, 4, or 1, 2, 5, 8, not on the other elements of a vector. You cannot do that with Neon, but you can do that with SVE. And then there's something called first faulting register, where you allow you to read past end of arrays, and without knowing how big your vector is and how big your memory is, and the hardware will say, no, you cannot do that. This is out of us. So just a quick rundown of different instructions. I think this will help understand what are the different capabilities. So I don't expect everybody to just memorize this or keep this in memory, but I just wanted to list what are the different capabilities. I showed the gather, load, scatter, store example earlier. There's something called vector partitioning, where you can partition a vector register based on the predicates. Fault tolerance, speculative vectors. Think about string copy. When we write code for string copy in C, I'm a C guy, so you just go keep copying until you hit the null character, right? But there's a way to do this faster. Is copying each one character at a time until you hit null is extremely slow. So there is a vector copy you can use, but the moment you hit the null string or go past that, the null character, you will get a fault at the hardware level. The hardware will say, okay, this is not legal. You cannot load this particular memory. And then you say, okay, that's okay. I'll stop my operations right here. So that's the first fault register capability. Horizontal vector operations is, we talk about vectors, two different vectors, you add them, you subtract them, you do whatever you want. But if you want to do operations on a single vector across on the horizontal side, that's called the horizontal vector operations. Prefetch, load store, so there is a big laundry list of operations it supports. Bitwise, for example, was not supported in Neon. Very interesting for certain algorithms. Reduction, does anybody know what is reduction? A reduction operation is where the code I showed earlier where you say R plus equal to a vector element, that's a reduction because you're reducing a vector into a single value. So plus equal to, when you reduce a vector to a scalar, that's called a reduction. And it's a very powerful, it's something called partial sums and sum of sums that is very useful in a lot of compression algorithms. They use reduction. And a good compiler can take advantage of reduction. So what is SVE2? SVE2 is probably the latest introduction in ARMv9. ARMv9 is the latest ARM architecture that's available today. I'm not aware of any specific chips that already supports ARMv9. But SVE2 is available in any ARMv9 instance that is going to come out. It extends SVE. It has a lot of capabilities to take advantage of machine learning, it delivers machine learning capabilities in the ISA, right? And then, especially at DSP side, because if you think about DSP operations, there are specific DSP operations like halving, rounding, saturation, accumulation, etc. Typical DSPs do that now ARM can do as well, because you don't want to go to a DSP for a certain part of your algorithm. It's much more expensive than what it looks, because DSPs live in a different world than a SoC and things like that. So I'm going to use a few slides to explain what is the SVE features. So, like I said, it can scale to the underlying hardware, which means that your code will run without having to recompile it, without having to tell the compiler what is the size of the vector on any hardware implementation. So, for example, if you look at this instruction right here, the .s says it's a signed integer, which means typically signed integers are 32 bits. Even on a 64-bit hardware, this .s means 32-bit. And what this says is add two registers, Z1 and Z0, and put it in Z2. Remember, I compared this to the Neon code that we saw a little while ago. The Neon code, it said how many elements are there. Here it does not say that. It only says the size of the element. It doesn't say how many elements. And how many elements is up to the hardware implementation. So, on the top, which is a 128-bit vector register, you add 4 elements. On a target B, which has 512-bit vector register, you add 16 elements. It's the same line of code that executes on both these machines, but your efficiency just went up by 4 times. So imagine a RGB processing algorithm that's running on a much more powerful phone that has a wider width. Your algorithm will be done 4 times faster than on a regular mobile phone. Predicates. Predication is basically another way of saying control flow, as in, what vector elements need operations to be done on. So for example, you have a predicate register that says, okay, this operation, I'm going to operate only on elements 1 and 2, not 0 and 3, right? And I'm going to add these 2 vectors. So what happens is, it'll ignore this. It'll only add these 2. And then in the result register, it's going to save the values 5 and 6. Well, why is it zeroing out the first and the last element? So there are 2 ways you can do specific predicates. You can say zero out the predicates that do not get chosen. So in this case, these 2 registers did not get chosen, the first and the last one. So the answer is going to be 0. If you generate an instruction that says P0/M, the results are going to look a little bit different. It's going to be just whatever is in Z0 at that time that will be preserved for the lanes that are not chosen. So what it helps is that what's called vector loop management. So you have some loops, you have leftover operations. So typically, if you do an algorithm, yes. Right. Right. Yeah, so the P0 is a vector register. So 0 means don't choose that lane. So it is not 0. Okay. So the predicate register is less like a vector register. You say which elements you need to choose. So that will be have the 1 bit. So this should not be chosen. So you have the 0 bit there. Should be chosen. So you have 1 bit, 0 bit. So this is going to only operate on these two elements. It will ignore this and this. Insert the predicate register. So this add operation, the previous add operation, if you remember, did not have this predicate register. Okay, this one has the predicate. So now it's conditional, right? Here it's conditional. It says only choose the lanes. Like you have 16 lanes, 4 lanes, how many other lanes in your register vector? Only choose lanes that have the 1 bit set. This is a powerful idiom because if you figure out, okay, this algorithm only has specific elements of an array, then it'll just generate one predicate, and then your whole operation is done. Instead of a complex control flow value, you can say, oh, is this index some value that control application. So where you basically do some operations based on not just the indices, but you look at two different arrays and say, okay, only if this condition is satisfied, I'm going to do this operation. Only if this condition is satisfied, I'm going to do this operation. Right? Otherwise, I'm going to do something different. So don't worry too much about the syntax of this. But the idea here is, first thing I want to point out is there's no control flow here in this code. There's no branch instruction on the right side. There's zero branch instructions. The Scalable code will have so many branches, it's pretty hard to follow, but the vector code on the right side is no branch instructions. The second thing is this condition here is captured through this compile greater than instruction. So it basically says, compare these two vectors and set these predicates right here. And then use these predicates to optimize further. So I want to point out that this is not hand. There is no this happen and do this. You have a optimization called auto vectorization that can actually figure this out. If you're interested in this, please ask me about it towards the end of the talk. So, vector loop management, I mentioned what is vector loop management. So, what happens typically is, let's say you can process 8 elements at a time, and your loop has to go through 11 times. So, what happens is you'll go through once. That 8 times you can take advantage of the vector instructions, but the remaining 3 iterations of the loop you cannot. So what you have is called a leftover loop. Okay. Not vectorized because there is not enough vectorization. And you have number of elements you're going to iterate on has to be a multiple of the data size. So in SVE, what it does is you look at index and say, okay, you don't have left-over loops. You stop operating once your loop count reaches a particular value because the predicate register will take care of that. So you register to say this is how many times you have to go. If you go beyond this, so in a SVE, basically you will have second iteration of the first iteration will operate on 8 elements, second iteration is to operate on 3 elements, three bits of this in the predicate register, and that's it. The loop will quit after that. No sequential code. So here's an example, right? So you don't know what hardware this code is going to run on, but the hardware itself knows half that information. That's how it scales. Because you're basically telling the compiler, you figure out how to generate code without knowing the vector length, how to handle the vector length. Here, the feature is much more complex than even the predication. There are I can think of 264, which is one of the most popular video encoder. I think I think Google uses a different algorithm for YouTube today, but I don't think H264 is very popular. And H264 does not just operate on linear arrays. It basically says, I want to operate on specific elements of an array. So I want to do the same operation on specific elements in an array. So it specifies different indices. So in this case, you want to basically say, I'm going to take elements 0, 3, 4, and 9 and operate on them. Neon can never do this. It's impossible for Neon to do it because the address is not scalar, it's a vector. So what SVE can do is you can load this into a vector, right? The Z0S into X0. The instruction is a very complex instruction. So take all this, put it into X0 and load from that register into Z1 using this predicate. So this pattern looks like this instruction. Extremely powerful idiom that's available in SVE. So we are right now look at the code, look at the C code that is there. It's impossible to vectorize normal ISA. If your instruction set does not have that capability, you cannot vectorize this. So for those who are familiar with vectorization, this is called non-affine transformation. So if you don't have a C here, if you just have A equal to B of I, your operation depends on the loop index. If you do have C of I, it does not depend on the loop index. It depends on something else that is based on the loop index. That's called a non-affine transformation in vectorization terms. So this is very, very difficult to optimize without proper hardware support. So I talked about a little bit about the first 4 registers. So the idea here is that you are allowed to read past end arrays, and the hardware will tell you if you did do that, and will stop the operation, and then you set a bunch of control bits that you can then use to control the execution. I'm not going to go into much details in this one. So we have 2 instruction sets now. One is called the SVE, which has got more capabilities, and then you have the Neon, right? Is it always better? Is SVE always better than Neon? No. This we have seen in practice. Neon has some smaller capabilities that SVE is not able to do today. For example, 16-bit by 16-bit multiplication, which is used in a lot of algorithms. SVE cannot do today. Which is a problem for 2 reasons. One, you need a much wider data to hold it. The second thing is the operation is more expensive because you're doing a much more expensive multiplication. In some cases, what happens is the control for vectorization is overhead is high. So you try very hard to do control for vectorization, it generates, ends up generating a lot of predicates. And that is not very good in many cases. So, and then the other one is a lot of computation do require extension. So you load a sharp type, you extend it to a word type, do operation on it. These kind of operations are very expensive in SVE. Similarly, if you take an example where you have scalar operations that you're going to use to construct a vector loop, no one can do that. SVE cannot do it because it has no idea what is the size of your vector instruction. So you'll just say, I don't know, I'll generate something, and usually it ends up, the compiler ends up generating something that's pretty bad. So because especially optimization that requires you, the compiler, to know how many are in a vector, cannot take advantage of SVE. So here is a simple table. You'll probably find this in, if you Google, but basically, the short is, if you ask me, it's two main features. So one is obviously the variable length of the vector register, support for predication, and then support for vector addressing is super critical. Again, it opens up opportunities for new algorithms to be written to take advantage of SVE. So in our compiler, we have something called a cost model. So we look at a loop, we have an auto vectorizer. We look at a given loop and say, okay, what is the best way to vectorize this loop? Should I use Neon? Should I use SVE? And we have a benchmark, internal benchmark called vector loops. Even if it's internal, it's mostly derived from open source. So if any of you guys are interested, I'll be happy to share the information. So we go on our compiler and we use a few like GCP, for example. And then we compare how good is the code, how is the Neon code versus SVE code. And we tune our compiler to choose the right one. So there are a few cases where SVE is not very good. For example, true recurrence. So if you have to write dependency, so you have to put something, and then in the next operation you use AFI. It's called read after write dependency. And SVE vectorizer will try to be greedy about this and end up generating pretty poor code. Some of the cases I covered, for example, sign extensions, to know the size of the vector registers, etc. So in these cases, we just say, okay, SVE is not good enough today. Let's not use SVE. So SVE is great, I would say, but it's a great headache for the compiler. Because LVM code, before supporting SVE, assumed all the register, it knows the size of the vector register. So it says that, okay, if you're describing a machine, for example, Neon vector unit in LVM, you have to go and say, what is the size of the vector unit? But now in SVE, you don't have to do that. So there's lots and lots of optimizations that assume you know the size of the vector register, and all the code had to be rewritten. Similarly, loop trip counts, that you can optimize for, if you know the size of the vector, cannot be optimized anymore. Leftover loops are much more complicated. If there's an operation that depends on like AFI, AFI plus 5, if these two elements are used in two different parts of the code, previously optimize it with Neon because you know the exact size of the vector, but with SVE you don't know the size of the vector, so you don't know if it's going to overlap or not. And then, as I said, some Neon operations don't have equivalent SVE operations. So SVE is a great, I would say. It holds a lot of promise. It opens up new opportunities for new algorithms and idioms. It definitely has much more scope for providing better loop performance, but it does, it does need a cost model. It's not a always a win. And we're just so hopefully, I or one of my colleagues can provide an update on how we are doing in this one. But this is one of the new stuff we are working on in Qualcomm at this time, and this is a very interesting area for us. Any questions? Yes. So you have what the predicate says is you operate only on these things, right? And then it says that in Z, which means if this layer is not 1, 0 is the result. And which is, if this layer is not big, don't change the result, preserve the whole value.
It's like one asking.
Yeah. So you can balance with either destroying the whole value or keeping the whole value.
My question is, can it have any bits? Any bits?
Yes, you can. Yes.
When they are about the environment, we always relate to the environment.
That's a good question, and I don't work on private people. So, well, I think one of the biggest advantages of ARM at that time was the power. ARM is still one of the top. ARM spec of microcontrollers and power. So if you go look at a microcontroller, which is, like on the ARM V4, V5 environment, for example, they have an extremely low power curve. So we showed that that power density almost relatively power. And mobile phone, there are only two most important things that people care about. The way you spend the mobile. Camera and battery. So I think you can provide a few phones with, it says it's not very well, because they're not able to get that far. Right, so power is, for mobile devices, super good. If you look at other domains, like desktop applications, for example, ARM is trying to get into those domains, but they are not able to get the performance there. Right. So power performance is critical in those areas. So for mobile device, power is super good. Any questions online? No. Any other general questions? I'll be happy to answer. Yeah. The what? More prominent than so you're not going to the compiler, whether it's, yeah, so you probably that, for 3 years the moment. Except we go use the open source company and we cannot generate it, you go to it. You can write different things, you can write one code as a but now, all the public is available to find. You can download it, you can buy it. So, you identify the instant generators. So it's a little bit challenging for the compiler without knowing the sign of the vector, but that part is already been taken care of by the application. Yes. How much the what? A lot. So now electronics has to figure out. So if you have a loop, right, it has to figure out the active path. Especially if it has to generate a predicate. So if you're operating A of I plus 0, I plus 2, I plus 4, etc., it's easier for the instinct to predicate. But if you do operate A of I plus X, where X is not known obviously, then it's still doable, but the predicate generation will be more complex. But the auto vectorizer, we have our auto vectorizer in Qualcomm is powerful enough to figure that out. I have some examples online, you can look at it, but they don't have any vector optimizations yet. Lots of optimizations available now. You know what an intrinsic? An intrinsic is, for example, if you have a instruction in C code, right? You can call a function called vadd, and the compiler will control the generated instruction. So intrinsic code is there, but if you just write a regular C code and add two vectors, that the upstream compiler can do today, without a Qualcomm compiler can do today. Yes.
On what? The vector? On what?
Designing the bigger is so if they get this phone, right, we will check your system. Whereas if you go look at performance, you just check when we are. So the bigger battery, the more battery for the more speed, so micro speed deeper. So it takes more gates, more area to chip. And so you're not going to spend, Congress has not going to put more area because it's interesting. They want more area because they're getting something. More area is for problem. So if you're using for designing hardware for high-performance stage where you don't care about you have strong cooling, etc., you can put wider vector. If you are like a mobile one, you're not going to do that. You're going to just say, I'm going to put the minimum, which is 128, and make sure the power does not go. So power, it's only hardware considerations, power and area. Yes. So you don't, right? So you don't know the size of it. So the compiler basically say, okay, there's a register called vscale register. So that will size, and that will be when the chip starts up, that register will be set to a pixel value, right? So depending on you can generate code to read that register and figure out, right? But it's a runtime operation, not an environment. Yeah. Any other questions? Yes.
There must be something which frequency scaling that affects AVDX cycle.
Oh, good question. I don't know the answer to that question though. Good question, not a compiler level question, because the compiler perspective, you assume that it scales nicely, right? So I don't know, I'm not having that, unfortunately. Yes.
The auto vectorization requires similar level performance to regular vectorization.
Etc.
Any other questions, please? As a application, now I call Dr. Evans, the present speaker, Dr. Raja Venkateshwaran.
Thank you. Thank you.
Thank you so much. It's really great to be back at Tech and share my thoughts. So, thank you for hosting me.
Now I call Dr. Chandrasekhar, Associate Professor. Thanks.
Thank you.
So, a lot to us. And I hope this interaction will the business of Qualcomm to the student community. This is a opportunity to thank our government, Dr. Nadraja, for trying to bring Dr. Raja to the campus. And many thanks to Dr. also who has shared his experience about the at Qualcomm and WTO is none other than Dr. Raja. And the total present here, not many lectures, but the person is working in a new area like computer design and computer architecture. And so thank you for coming out today and giving us this particular talk. And here, when we talk about this particular title, for those who are not much on what it's all about. And with that, knowledge has been related by your excellent talk, with that it's amazing. 1.2 million kinds of limitations, why we have SVE, why we want to get SVE. So thank you so much and thank you everyone, the faculty and the students who have been very attractive and interactive with the speaker. Thank you once again and have a great day. Thank you.